Good morning, everybody, and welcome. This is Professor Thayer with you from my breakfast table. Plan today is to have a PCAM marathon and see how many more of our lectures we can get done in just one day. If I work for 12 hours today, an hour and 20 apiece with 10 minutes break, that means I could do 8 more lectures today. So here we are at the breakfast table in my house. Good morning. Join up, bring a bowl of oatmeal, and join up, and we're gonna now talk about our next lecture, which is entropy and the second law of thermodynamics, our next lecture in the thermodynamics section of our course. So let me hide this, share screen, and the usual thing. All right, share screen. And now let's come over here to the public screen. All righty. So we've been talking about thermodynamics and the first law of thermodynamics, which essentially says that energy is constant. It's neither created nor destroyed, but it can change forms. And in thermodynamics, what that means is changing between heat and work. Now, today we are going to explore some of the aspects about the entropy. So entropy is about the disorder in the universe. So the second law is going to govern the system or reaction, whether it will go or not. The direction of the evolution of the system is going to be given by the second law. So we have considered energy, but that alone is not sufficient to determine if the system is going to evolve in a particular way. So the disorder of the system must also be considered. And this, in a way, is a lot of what was going on when people were doing thermodynamics. You might have heard of the Gibbs free energy equations. I do get a little bit ahead of myself here, but let's just pick a pen here. Great. Delta G equals delta H minus T delta S. So essentially we have already considered the internal energy part, which is represented in this equation by the delta H part. That's, I know it's a different letter and we'll get into the relationship of those. But, people wanted to understand why delta H was not always telling correctly whether something is going to go or not. And the reason is because they missed the second half of the equation. And this half right here is the entropy part of the equation. So you have to figure out if it will go. You need to consider both energy and entropy. All right, so some evidence that energy alone is insufficient to determine if a reaction or process is spontaneous. And of course, will go is what spontaneity means in a more sophisticated way. Some evidence that energy alone is insufficient to determine if a reaction or process is spontaneous. The energy only view, which by the way is wrong. But imagine you were the scientist trying to figure all this out. You might have been thinking along these lines. Iron rusts, but it doesn't spontaneously unrust. I have a rusty item that had been stored in a damp basement. It's not going to spontaneously unrust. It will unrust by me sanding off the old rust and refinishing it. Okay, 2H2O. Oh, no. 2H2s plus O2 goes to H2O. Explosive. Very spontaneous. Oxidation. But the reverse. 2H2O breaking down into 2H2 plus O2 requires energy. This is called hydrolysis. Basically electrocuted, and it might do that. So this means that to go a reaction must be exothermic. That's to tend to the lowest energy. All right, well, let's consider a counterexample to the energy only view. Spontaneous processes. That's not spelled right. That are not exothermic. Also go. So, for example, we might have a system like this. Let's consider some gas chambers. Gas chamber. Like so. They're equal on both sides. We'll have an initial and a final. These are the same gas chambers and they're exactly the same size. Something like that. Okay. And so we might have some more gas in here. There's going to be a stopcock here. Then we go like this. Okay, stopcock. And we have some blue one. Dyed blue. Okay, and this is a vacuum. There are no dots in there. All right. And then we have stopcock. so when the stopcock is in that orientation, okay, this one is closed. Here it is open, in case you couldn't tell. Okay, and what happens is the gas will distribute between both and be less dense. For volumes, it will be half as dense as it was to begin with, right? Okay, there we go. Yes, evenly fills two chambers. Yes, on one side. There we go. There's no energy change. This happens spontaneously. Oh, that's true. The reverse, according to thermodynamics, isn't impossible. But reverse has never been observed. All the gas, when the stopcock is open, jams over to just one half. Not gonna happen. So gas will not spontaneously go to just one chamber unless there is some sort of input or work, right? So if we go in this direction, work required. It would be nice if things just went over as I think so. Probably not going to happen. All right. There's a number of other counterexamples. You can probably think of even more. Mixing liquids. Dispersion of solute in solvent. Soluble solute. Like sugar dissolving in water or salt dissolving in water, something like that. Barium hydroxide. With ammonium nitrate. Have you done this reaction? It's the cold pack reaction. You ever had a chemical cold pack? This is what it is. It's true. We used to do this lab in Gen Chem at FASA. So we can conclude from the counterexamples that some other factors besides just energy is required to determine whether the reaction is spontaneous or not. And the counter would be we may conclude other factors besides just energy. Are needed to determine the spontaneity of reaction. All right, and that's why we have these. All right, so now we're going to consider lattice view. This similar to the lattice view of a protein that we had earlier. Entropy. The lattice view. Consider that like the gas chamber. that we had just before. Suppose each chamber contains a volume of 2 units, represented by 2 slots of, and each chamber has a different gas represented by the symbols X and O. How many ways can you arrange the system? All right. Let's do it like this. And then divide this in half. So we have one chamber here. Again, doesn't really look, my artwork is imperfect. Let's see, maybe we could get it a little bit more. With the lump on no idea what that point is. Okay, and then we have another gas chamber over here. Again, this is exactly the same as the one on the left, identical in all respects. All right, and we're gonna add stop clock, and we're gonna add stop clock open. All right, and we're gonna have lattice view. So we're gonna have 2 units of the gas in here. Okay. And it's gonna be like this. And what we're gonna do is we're gonna enumerate all the possibilities of ways that things could be arranged in there. Okay, so here's the gas, X and O. Okay, so what this means is we have, okay, we should probably just make a note of what our setup is. Okay, there's 2 gases, X and O, and there are 2 units of gas on each side possible, right? So the vacuum is the empty, is this thing. Okay, so what this says is that there could be 2 units fitting over in each side, but there's only 1 unit, and there's an X on this side, and there's an O on that side, 2 different gases, some hypothetical gases. Okay, got the setup. Now what we're going to do is we're going to enumerate all the ways that we could arrange the system. How could it fill the space? So the reason why this is a lattice problem is because we have 2 places where the gas could sit. Of course, in real life, this is a continuous problem. Okay, so what we're going to do is, all right, so the X could be on the left and the O could be on the left as depicted there. The X could be on the left and the O could be on the right. All right, now the next thing is we could have the X on the right and the O on the left. And we could have the X on the right and the O on the right. So this means the number of ways this could be arranged is 4 ways. Okay, now the open chambers. Okay, so here we'll begin with an X here and an O here, but because these are open chambers, guess what? The gases could move between the chambers. Okay, so it's like this. Okay, we're gonna have to be very careful about the combinatorics. And actually, this one has a lot more. That's the point of this. Okay, so we could have, yeah, we have 4 positions and 2 gases that are different. So we could have XO. So the X is on the left, and then we could have X and the space, and the O could move over to this side. We could have X here. So you see what I'm doing? I'm holding this one the same, and the O could move over to here. So there's going to be, in other words, 3 ways per position of X. Okay, so the X is staying in the same place just to help us keep track of things. All right, now what we could do is we could do the series where X moves to the second position. So we do 1, 2, 3, 4. It should be Okay, so X could be here. O could be here, here, or here. All right, that's this set. And now our next set is like this. X could be, and you're probably starting to guess this by now. Oops, yeah, they're all the same size. Yes, okay. X could be sitting here. And then O could sit here, here, or here. It's kind of like tic-tac-toe, but not quite. All right, there we go. And the final combination could be like so. You could have 3, 4, 1, 2, 3, 4. And guess what? X is here, and O could be here, here, or here. Oh, that's a lot of combinations. All right, so let's just make some notes about this section, but just so we're clear that that pertains to this part over here. So, all right, W equals 12 ways to order this chambers. Okay, so this stuff pertains to this one over here. Right? Yeah, okay. So how we're dividing that up for this chamber. And we have also talked about, so we separated out. Now we need to do some little calculations here. Okay, so this has 12 ways we could arrange it. This has 4 ways we could arrange it. Now, we have this equation that tells us how we could order the system. It's an entropy equation, and it has a log in it. All right, so what we're going to do is we're going to calculate the entropy. S equals negative KB, the Boltzmann constant, LNW, the number of ways. This equals negative KB ln4, which is equal to negative 1.38 KB. So you might say, oh, but you can plug in the number for KB. Yeah, you can. You can substitute in the KB and make this all numeric, but we might just compare it in units of KB, like multiples of KB, which is why we're leaving it like that, which is the way that oftentimes you'll see that. Okay, let's take a look at how it would be over here. S equals negative KB ln W and equals negative KB ln 12 equals negative 2.48 KB. So what we see is that there are many more ways to order the system, and it has much greater entropy. All right, so let's just zoom out for a sec. So what we've done here is we've made the lattice model, and we looked at the combinatorics of how the gas could partition itself between these. And we see that when the stopcock is open, there are many more ways that the gas could partition itself. This is the idea of entropy, and this is why much more entropy over on this right side when the stopcock is open, and there are more ways that things could arrange, even though the number of slots is exactly the same. The entropy is much greater, and so the reason why the system will spontaneously proceed from the divided one over to the open one is because there is much more entropy, and the system would be quite a lot more happy to be like that. All right, so maybe we should just capture some of those thoughts. More ways to order the system. Let's do greater entropy. All right. That's why gas fuels spontaneously. It's opened. This spontaneously makes. There it is. Let us continue. So the entropy can be considered as just ordered, interpreted from the combinatorics of the states of the system. The entropy is more favorable for a system with more ways of ordering itself. Okay. Now we need to talk about the state function nature of entropy. Next topic. Entropy is a state function. All right, remember we did the path integral diagrams. I had something like this. We did some PV work. We did this one. Start and we did this and then like so. This was actually divided into two sections, and we have this and that. All right, so we had this A and B, and we had this line right here. This is the isothermal. This is reversible heating. And this is reversible adiabatic. One. Okay, this is the Q equals 0, and so delta T equals 0. Remember this one? Okay. So we have a general formula. The change in entropy is equal to the integral from 1 to 2 of dq reversible over t. Now what we're going to do is we are, oh, this is path C. This one needs to be labeled. Okay, so what we're going to do is we are going to now consider all the various paths, just like we did before when we were talking about heat and work. Okay, so the first one we're going to consider is path A, which is this isothermal path. The heat of isothermal expansion. Q of A. It looks like a subscript. QA, EQ. So rev A is the subscript equals nRT to 1 over V dV. What's nRT over V? V equals N RT, right? And we have nRT over V. What we did is we solved for P, okay? That's basically what this is. It's P as a function of V equals nRT over V. You're gonna see this a lot. P as a function of V equals nRT times 1 over V, in other words, okay? This is what's going on here. We made the substitution. So we shouldn't get worried about what happened here. For path A, delta S of A equals 1 to 2 dq z of A over T1. Now we're going to sub for Q A. So delta S A equals, now we're subbing in volumes, and that's because, well, we just said this is a function of volume, right? V1 goes here and V2 goes there. And RT1 over V dV over T1. That's because we now took this and yeah, this part right here got substituted into this thing here. Yeah, that's what just happened. Okay, then we're going to simplify and cancel. So delta S sub A equals V1 to V2 and RT1 over V times 1 over T1 dV. Wait, that does not look right. That should say 1. Okay. And okay, so what happened? Division is multiplication by the reciprocal, right? So that's what happened there. And now the T1s cancel out. Terrific. So now we're going to factor the constants. Oops. Factor the constants. Delta S of A equals NR times V1 to V2, 1 over V to V. Okay. These are the constant parts, and we're doing dV, so that's why volume's got to stay on the inside. And then we integrate. So recall 1 over x dx equals ln x. Remember that from calculus. Delta SA equals NR ln V on V1 to V2. So now how do we solve this thing? We do the upper bar, evaluate integral on the limits. Okay, so we'll do this delta SA equals NR ln V2 minus NR ln V1, right? So this is the upper minus lower. Right, this is how we do calculus, right? Okay, and then we simplify with the laws. Okay. So delta S sub A then equals NR times V2 minus V1. All right, so that's factoring. Factoring. All right, equals NR ln. Now remember, the laws of logarithms said that when you have a subtraction, that it turns into V2 over V1, like so. It will be a subtraction. So V2 should be on top and V1 should be on the bottom. Ta-da. If you switch the order of these, it makes a negative sign up here over here. So if you didn't know the order, you could switch them, but there's not really a reason to change that here. Okay. So today we have finished one. No, unfortunately, I don't remember the colors we chose the last time for this, but let's assign some colors. How about this one is going to be blue today? It's path A. And here's the answer for path A down here. This is what entropy is going to be for path A. All right, great. Now the next one we're going to do is we're going to do path B plus C. Oh, let's pick some colors for path B and C. All right. Wait, that's what I said. B. It's here. Okay, so how about pink? All right. And C will be a related one. That'll be this purpley color. All right, so we have them being related shades. And now we're going to do path B plus C. Path B plus C. All right, so we're going to do delta S B equals, that's not a Boltzmann B, that's a regular B, equals the integral from 1 to 2 of dq rev E over T equals 0. It's adiabatic. Why? It's the adiabatic. There's no delta G. There's no delta T. Okay. So there's no heat contribution, right? LT, that equals 0. Okay. That one was easy. No heat, no heat change. That's 0. Okay. Delta S plus C equals the integral. All right. We get this going in the opposite way. And that's because, remember, this is the path that goes up. Yeah, that's why it's like this. dq rev C over D equals. Now we're going to need to integrate over the temperatures, T2 and T1, C sub V of T, V of T over T dt. equals. No, I'm going to play a trick. D1 to D2. Notice that we switched, right? Notice this happened. Okay, switches the sign of the integral. C sub v of t over t dt. And then we'll solve this, right? So this is basically like we subbed in C sub v of t equation, switch the order limits. Okay, and then we're going to solve the integral. C sub v dt equals negative. Is it that one? Yeah, equals NR ln V2 V1. So you might be wondering, wouldn't this be T? And not V? Let's just explore that for a second. It has to be V. It is V. Delta S sub A equals delta S V plus C. One would think, but according to it's the V. Okay. So for E plus C delta, okay, write the sum. Delta S of B plus C equals delta S of B plus delta S of C. This is the sum. Pretty easy. And we're going to substitute the answers from above. Delta S of B plus C equals, okay, what did we get for the first one? The answer was 0. Let's just go back to how this fit to our little picture. B is this little pinky thing. All right. So what we probably ought to do is just keep track of these. That was the pink one. And B was the easy one. The answer is right here. Okay. And path C was the more purpley one. The purple one. And what I should probably do is, since this is the formal one, I should write delta S sub C equals. There we go. All right, so now I'm just going to substitute in the answers. Equals this B is 0 plus NR ln V2 over V1. All right. In other words, delta S of V plus C equals NR ln V2 over V1. Now, you could compare delta SA to delta S of B plus plus C. So although the heat Q was different, the delta S is the same. Remember we talked about those state functions. Delta S is a state function. And it's great that we wrote it as a capital letter. All right, now, entropy is the driving force for the movement of heat. Why does heat move from hot to cold? Well, similar to the gas that we talked about. Let's take a look about some insulated chambers. 1, 2, 3, 4. 1, 2, 3, 4. Great. Attempt at making this sort of I just in the audience here. Okay, this is insulated. Okay, so I'll just insulated. Oh, great, great insulation. It's insulated. Cooler. It's my lunch cooler. There it is. There. Okay. And in this system, we have temperature A, temperature B, volume B. Two family insulated chambers. That's volume. What does that mean about work? Maybe more work is possible. Two compartments are generally replicate. So in other words, heat can go across this. Okay, so we should just make a note of that. And Q's can go across. We'll put some Q's here. Indicate the Q heat could go across. The two compartments have different temps. All right. I wonder what will happen. That's total. Equals S sub A plus S sub B. S total equals D S A plus D S B. S total equals U, the internal energy A over 2A B. The entropy of the system is related to the energy. So if TB is greater than TA, UB is less than 0, energy flows as heat. In other words, right? So TB is greater than TA. That means that this be the hot side, this be the cold side, right? Goes TB is no, that's backwards. I messed that up. So maybe I should not let it go. Let's get it straight. Okay. So if TB is greater than TA, yeah, this is the hot side. Hot and cold. TB is greater than TA. TB is greater than TA. Right, that's hot and that's cold. All right. So how will the energy flow? From hot to cold. So therefore, ds is greater than 0. Energy is heat flows, so as soon as something flows, the entropy increases. Energy is heat. We know this. Energy is heat flows, and as soon as something flows, the entropy is going to increase. The same argument holds for temperature. No matter which one is going to be hotter, always going to flow, which leads to an increase in entropy, right? Just like the gas chambers we looked at. So a few observations on entropy. Although energy must be conserved, entropy is not conserved. The entropy will spontaneously get greater for spontaneous processes, in an isolated system. And we could make a graph. Okay, so here we have the entropy, and here's T for time. And it's the time when we have our time, we will start with the chamber down here. And stop clock is closed. We have something all down here. Gas, oh, it's kind of bled over. The gas is just in one chamber. The entropy of spontaneous processes increases over time. So we have right, for some S max, and here is our S0, right? And so in the middle, so this is what this looks like in the beginning, and then as we are in the middle of the process, what happens? We have some gas here, but it's starting to populate over there, but there's more gas over here. Mixing is occurring. And then we have, in the end, both chambers are equally full. Equilibrium, and this is why the entropy reaches some maximum value, right? So there's no more mixing, right? So the mixing stops. So when equilibrium is reached, then the maximum disorder is achieved, and there's no change in the entropy. It's kind of like heat death of the universe, right? Entropy is always increasing in the universe, and someday everything will reach equilibrium, and that will be the end of life as we know it, and the universe will no longer go. All right, so next thing we want to talk about is the Carnot cycle and the heat engine of efficiency. Very important for a variety of reasons. PYCLE and heat engine efficiency. Very important for the Industrial Revolution. Okay, developed in the 1820s to study the efficiency of heat engines being invented as part of the Industrial Revolution. It was used to describe the maximum possible efficiency of a heat engine. They're not very efficient. It's the answer. Okay, schematic of a heat engine. All right. So we have hot reservoir. It's the heat engine. And here is the cold reservoir. So trains used to work so the electric out, but we probably seen working like this. Okay, what's going on here? There's a train engine. There is have the great big wheel and another little wheel down here. Light. So guy driving the train operator. Yes, maybe it's even a girl. Okay. And in here is the important part for our lesson. So the wheel is has some drive shaft on it with this piece. Okay, it has it's kind of like this. This is mechanical engineering. They may be a little upset about that picture, but more or less, this is how it works. Okay, there's a piston in here, and there is a fire. Let's see if I can find my fire pin. Oh, yep, that's great. Right down here. Okay, this is how it works. There's a fire in there, right? And there's a piston that is going up and down. Piston is right, but the piston, instead of going up, yeah, this is the thing. The piston is attached on the bottom side, not the top side. So that, yeah, you see what's happening here? There's a cylinder in here, and the cylinder is going up and down, and that is driving this the train wheel. That may not be completely accurate from the point of view of our mechanics friends. I'm not totally sure exactly how train wheels are hooked up, but something kind of like that. All right, and this is giving off some smoke, polluting the environment. Pollution. Okay. This is work as mechanical energy. All right, so here we have our hot reservoir to cause the expansion. Right, cause expansion. Here's the heat engine. This is so here we have Q H is plus, right? Input some heat. Okay, and here's our heat engine. This is the system. And here we have the output from system, ROM output, and it goes into cold reservoir. Let the heat out. So the piston the next round. So usually this is just the surrounding air, right? This is just usually heating things out. Things, TH, right? TH, this should actually be TH. Not a side note, that's a key thing. And Q sub C is negative. Okay. The heat going in is positive, heat coming out will be negative. And the output from the system is full reservoir. So we're thinking about like the train. We even have some train cars, right? There it goes. And railroad system. Yeah. There you go. All right, cute diagram. Okay. So the fire in the engine causes the piston to move up. To move up. Expansion of gas. Yes. The piston is coupled to the drive wheel. On the train, and let's drive. So the total energy is given by the sum of all heat and work. Delta U in equals work plus Q of hot input plus Q of cold equals 0. So some of the input heat is converted to work, and the input equals the output. The entropy is given by heat divided by T for the two temps. Delta S engine equals dq rev H over TH plus dq rev T over cold temperature equals 0. The energy is drawn reversibly from the hot reservoir. Heat passes through the engine. Which does work. Heat left over is discharged to the cold air. Signs are written with respect to the engine. With respect to the engine. As it's defined as the system. QH plus because the heat input sloppy. Heat input heat input to the system. And you see there's negative, which is the heat output, heat exits. Efficiency then can be expressed in terms of temps. H minus DC over TH equals the efficiency maximum. And so maximum efficiency can be written in terms of temperature. Temperature, max efficiency. Equals negative W over Q H equals Q of H plus Q of C over Q of H. Equals H minus TC over DH. And finally, the entropy can be expressed in terms of the partition function. The entropy of the system equals negative KB times summing over J, EJ, ln EJ. This looks like the Ways equation that we had seen earlier. When the system is completely ordered, all the particles are in the ground state. Ordered system. S equals 0. Then the entropy maximum happens when they're all equal. So we saw this, right? The ordered system is like when we have the gases, right? We have it closed, we have this, right? Like that, right? And then the disordered system is when things are moving and they are now equalized. Disordered is as the entropy is greater than 0. So this is like, once we have opened the gas chamber, right? And gases are equally on both sides. And we saw this when we had that sigmoidal curve, right? It's the same thing. So entropy then can be expressed in terms of the macroscopic partition function. So we could write it like this: X equals KBT dln over dt with n and v, n being the number of particles. So we should probably note that number of particles and volume. These are being held constant. Plus KV ln Q as formula. One can cure a Q of choice, such as monatomic ideal gas. All right. So what you do is you substitute in this Q produce the partition function of choice. So this links back to when we talked about the various partition functions, right? Remember we talked about partition function for the monatomic gas and for the diatomic gas and so on, right? And we had some different equations for that, and you could break it out for rotational, vibrational, and so on, right? Whichever Q you want to use, you substitute in your Q. All right, so then, what have we talked about today? We have talked about a number of interesting things. We have talked about entropy and the second law of thermodynamics. The entropy of the universe is increasing. That's basically what today's lecture is all about. And we saw how to do that using a lattice model and some gases in a chamber. So we all know that if you have gas partitioned into one side of a chamber, and then you open the stopcock, that it's gonna mix, no big surprise. But we wanted to do this out in a lattice way, which is what we did here to demonstrate quantitatively what the multiplicity of the system would be. So we could do a lattice model of this. And here we have the X's and O's, and we saw how they distribute. So there's a lot less ways you can order X's and O's that are partitioned versus if they have equal space amongst each other and they move apart. All right, so this means that there's more ways to order the system and there's greater entropy. So when the stopcock is opened, it will mix. And then we also wanted to take a look at entropy and state functions. So we're back to these PV graphs that we had looked at previously for heat and work. And so we considered the various paths through this in order to consider whether entropy is going to be the same going to the start to the finish versus going on path A or path B plus C. And so first we solve for path A. We remember this is an isothermal path, and we got out that delta S is NR ln V2 over V1. But for path B plus C, first of all, we noticed in the adiabatic one that the entropy contribution is 0 because there's no heat change. But path C is a little bit more complicated, has a equation that actually is pretty close to the first one. And so then we wanted to compare the two. So although the heat was different, the entropy would be exactly the same. So this is a state function, and that's consistent with us representing the entropy as a capital letter. We also wanted to see about entropy in a situation where you have thermocoupled bodies. So entropy is the driving force in the movement of the heat. So we saw when we have an insulated system and you have two temperatures and two fixed volumes, that the heat will move from the hot body to the cold body, which really isn't a surprise, but we're able to work this up then in terms of the entropy. So the change in the, if TB is greater than TA, then the change in the internal energy will be less than 0. That is that the energy will flow from the hot thing to the cold thing, which makes perfect sense. We also saw that we can make a diagram of this. And so again, that stopcock with the gases in it is really useful. So we can start off with the partition situation, and over time they will mix, but it will come up to an asymptote because you can only unmix so much and you'll reach equilibrium. So in this case, the change in entropy will stop, but as soon as, until you reach that maximum entropy, there'll be a drive forward for the entropy to continue. Then we saw the Carnot cycle and the heat engine and efficiency. So we're able to understand this as a hot reservoir going to a cold reservoir with a heat engine in between. And for an example, we had a piston being driven by like you would have in an old-fashioned train. So this is work as mechanical energy as an example. Typical example. And so what we saw is that the total entropy is given by all the work that's done, and heat gets put in, and then heat comes out and work gets done in the middle. And so we can then compute our efficiency. And so we can do this in terms of the temperature. So unfortunately, heat engines are pretty much not very efficient because they give off a lot of heat and not as much work as we might like. But the maximum efficiency would be the negative W over Q reversible, which we can write as this equation here. It's TH minus TC over the hot temperature. And finally, we saw how this relates back to those partition functions that we have been talking about. So this goes right back to the lattice models, and we can see that the gas will partition as we did above, but you can substitute this into the entropy equation now using the partition function. All right, well then, thank you very much for joining us, and we are right on time for an hour and 20 minutes. So thanks for joining me for today's lesson on entropy, and it's been an hour and 20. So great. We will see you soon. Bye-bye.